Good morning. Hello, everyone. And super happy to be here today with you at SPS. So my name is Maurizio Granato, and I'm representing Industrial Automation Robotics team for analog devices. So I've been in the semiconductor industry for over 15 years now, and it's always a pleasure to be here at SPS in the presence of such a broad industrial community. Today, the topic of the presentation is industrial robotics and the new era of radical change. So what's happening in robotics and how semiconductor and industry can change this world together. So to start with, what I'd like to touch is the transformation in industrial robotics as a whole. So I would like to start from the high level. The robot has become the epitome of the change, the icon of the transformation. And this is especially impacted by 4 key elements that I'd like to touch as megatrends. The first one, and that it's obviously on everybody's mouth, is artificial intelligence. But why is everybody talking about AI? Why artificial intelligence is so important for robotics? Well, the key reason is that robotics classically had 2 classes of challenges. Number one, it was the challenges in terms of deployment. So how complex it is, how long it is to put together expertise in the application and expertise in programming a robot. And AI can be clearly a way to overcome that. The second challenge is the wide range of tasks that a robot can cover. And so the adaptability that artificial intelligence can bring has a significant impact on such vast class of challenges that can be covered. So AI is now bringing the potential for fastening and speeding up the deployment of robots in the area of industrial automation. These can only be importantly deployed when you have self-aware automation. Self-aware means that the robot will be actually capable to understand what's going on around them, what's happening in the system, what's happening if there is a human going by, if there is a safety problem, or if there's an adaptability challenge that has to be reacted to. And so because of that, we can see that robots are now becoming from highly automated to autonomous machines. And that's this autonomy that will actually create a reduced dependence on workers and fundamentally increase the productivity of the factories of the future. The third key trend I'd like to touch is sustainability. How is robotics impacting sustainability? I mean, you might say, well, you know, robots consume energy, so why is robots helping sustainability? Well, remember that there are a couple of aspects that are really helping sustainability from the robotic standpoint. Number one, the increased yield and the lower amount of waste that are generated by highly automated products. So this is a very important factor to reduce the waste and increase the sustainability of robotic automated factories. The second aspect is also improving the quality of life of people, because these will allow us to not be any more subject to dull and demeaning work. And so those 2 aspects of increasing the yield, reducing the waste, and improving the quality of life of people are very important sustainable factors which are driving the adoption of robots. And last but not least is the digitization. So all our factories today, I'm sure you guys have seen many more sensors, many more data coming together. All these sensors are fueling the revolution of AI and machine learning that we were talking about before, and these automation with self-awareness that can be enabled by that. So in this context of these 4 macro trends, I want to go one level deeper and talk a little bit about the robotic revolution that is happening now. So what I'm going to start with is just a very short recap of the history, because you might say, Maurizio, why now? You know, what's going on that is making robotics so interesting? Well, robots have been around for a while, right? I mean, in the 80s, in 1980, there were already 4,000 robots deployed in the factories. At the time, robots were fundamentally leveraging the fact that there was lower cost processing power available, more memory, more programmability available, and so robots were used fundamentally to implement complex tasks with very high level of repeatability. Over time, what happened was that in the last 10, 15 years, we started seeing collaborative robots. Collaborative robots are a new concept where, through the use of increased sensorization and increased safety, you fundamentally have the capability of the robot to work alongside humans. And so now we start having much more complex safety architectures, robots working closer to humans, less requirements for metal cages around the robots. Of course, this is making the robot not very different looking than the robots of 20 years before, but what's changing is the background. The IT/OT infrastructure of the factories is now collecting much more data. There's a much stronger data backbone, and all these data are now creating the input to the AI revolution that we were talking about, because high-quality data are giving us this chance to train the robots and make the robots much more autonomous through the sensorization data and through the actuation that they can leverage in real time. So speaking of data, a report from McKinsey showing the potential for $1 trillion economic impact of generative AI on industrial productivity. So, I mean, everybody's talking about AI, but can you give us some real examples? What are the real examples of AI in robotics and industrial automation? Well, ADI has already seen at least 2 or 3 cases where AI is already having a heavy impact into the industrial world. The first one that I'm sure all of you have seen, even at this show, is condition-based monitoring. Predictive maintenance, leveraging vibrations, leveraging current and voltage sense information from motors and from assets, is already leveraging the capabilities with AI and with ML to increase the detection of multiple sensing modalities and multiple failure mechanisms. And so not only is telling, well, your motor is failing or not, or your asset is failing or not, it can tell you which is the kind of failure, where you have to go and react in order to save your lifetime of your asset. Second example is object identification and classification. Mobile robots are going around factories and they have to navigate, they have to distinguish if there is a shelf, or if there is an object, or if there is a human. And in order to do so, AI applied to vision and to depth sensing is becoming much more ubiquitous, and it's really giving us the capability to further increase our understanding at a robotic level. And the third example is adaptability and loop tuning. So what we are seeing is that if you have a humanoid, or if you have an AMR that has motors that have motor parameters, now these motors can be adapted in real time. They can adapt to different terrains, they can adapt to different slopes. So the adaptability is another key concept which is really enabled by machine learning tools. So the physical example that we see in the world of AI right now is the humanoid. I'm sure you guys have seen plenty of videos on YouTube of humanoid robots doing all kinds of complex things. They thread needles, they cook. I mean, of course, it would be great if they, they remove the mess in our houses. But the #1 application for humanoid robots is definitely industrial automation. Plenty of analysis are showing that the first deployment of humanoids will be in factories. So factories will be deploying humanoid to really replace what are defined hard to automate jobs. Connecting wires, moving pieces of metals from one place to another. These are really tough tasks to automate. But how can you achieve this level of autonomy? Well, of course, first thing we would think of is heavy digital brains, the digital compute part which is driving these robots around. Yeah, sure, that's true. But the second thing is these digital brains, they have to connect to something, they have to sense something. And so the examples that we have here are including the perception of the environment. We're talking about vision, we're talking about depth sensing to determine the distance of objects. We're talking about current and voltage and magnetic sensing. We're talking about angle sensing and pressure sensing. If you want to grab this glass of water in order to be able to drink, you need to make sure that you're not breaking. And so because of that, you need a force sensor to do that. Actuation, of course, is another aspect. So you need to very precisely move. And now you're seeing new classes of motors at this show, which are really miniaturized because now you start to have to do the actuation of a finger. And of course, efficient battery management and power solutions. These are very important because these humanoid robots will now have to sustain a work shift. So how do you sustain 8 hours of work for this humanoid? Today is very difficult. But the key to get there is more efficient power management and lower power consumption through all this sensorization. And of course, once you start to sense and actuate all the robot, you have to communicate. And so the communication between the central brain and all these actuators is very critical to be done in real time, meaning very low latency. So the way Analog Devices is mapping as a blueprint this set of technologies that are needed for all classes of robots, and humanoid is only the key overall example, but that's covering all classes of robots, are what we define connect, control, and interpret. So if you look into connect, control, and interpret, they really give you the blueprint of the functionalities that I mentioned before. The connectivity is bringing the information from the actuator, from the sensor, back and forth to the digital brain. And you want to do it with very low latency, otherwise there's going to be too much delay and you are unable to implement the task that the humanoid or the other robots are supposed to do to achieve the safety. The control is really about effectively managing the movement of the robot. And finally, the interpret is to detect what's going on. And to detect doesn't only mean vision, as I mentioned before. It means audio, it means other sensing modalities. The classical examples that come from a semiconductor company like Analog Devices are the ones that are listed here that I'm going to briefly mention. But please bear with me because I'm getting to the last part of the presentation, which I think is going to be very disruptive for robotics. So what traditionally you would have seen in the semiconductor space is that you would have technologies for each of these areas that I mentioned before. You would have seen time-sensitive networking, TSN Ethernet, that is bringing gigabit Ethernet capabilities to the edge. You would have seen GMSL technology, which is bringing 6 gigabit of upstream and 200 megabit of downstream if you want to bring a new camera sensors information to the central brain. You would have seen wireless connectivity solutions that are allowing you to communicate without wires, which could be at short distances or at long distances like 5G. From the control perspective, we have technologies that would cover either the low voltage space, like the Trinamic portfolio in the stepper motor or brushless DC motor, which is really allowing you to have very fine control of the motion without any need of lines of code with, for example, hardware field-oriented control. And you would also have high voltage control, things like integrated isolation technology that would allow you to play with 650 volt GaN or 1200 volt silicon carbide devices for strong miniaturization. And then on sensor fusion, Analog Devices is offering technologies like 1 megapixel depth sensing cameras or 77 gigahertz radar solution. Okay, so that's understood. Those are the classical examples. So what's new? What's the change? Well, in the context that I mentioned before, what Analog Devices is doing is that it's putting themselves in a new position of offering subsystem level solutions that are significantly speeding up adoption of these technologies for the robotic world. So some examples are here. As you can see, we're not talking anymore about a chip level product, but we're talking about a subsystem level product, which is intended to accelerate the adoption of these technologies into the robotic space. Examples like 60 gigahertz wireless connector for mechanical replacement. This doesn't need any kind of know-how in terms of antenna design or wireless RF. It's coming as a module that you can buy and put into your system right away. Other examples like sensing modalities like depth sensing. It's coming as a subsystem, which includes lenses, it includes calibration. It doesn't require any know-how in terms of optical. Things like motion capabilities or angle sensing capabilities, where we offer technologies that are capable of having multi-turn angle sensing that has true zero power. So if the power goes down and it comes back again, you will have still the maintenance of the information of the angle without any need for you to know about how to design a magnetic system, how to design an angle sensing solution. So as a whole, you can see that the transition that Analog Devices is doing in the semiconductor space for robotics is fundamentally to acknowledge this rapid acceleration of deployment, and in doing so, it's creating new classes of subsystem products that you can embed into your robotic system in order to speed up your deployment of robots for the future. So to conclude, I would like to remind 3 key points of this presentation that I mentioned today. Number one, is really the fast transition of robotics from a very repeatable kind of concept for complex tasks into a highly autonomous machines. So robots are becoming aware of their environment and taking autonomous decisions. Number two is the AI impact into that, and the acceleration, number one, in offering wider and more complex tasks, and number two, to lower the cost and the length of deployment of robots in the field. And number three, of course, the way that ADI is going into this wave of new robotic subsystem and ultimately accelerating the deployment of these technologies for a faster turning point of robotics right now.